It's a pleasure to have today Hao Jia from the University of Minnesota, and he will talk about long-time dynamics and nonlinear inviscid damping for 2D Euler equation.
Thank you, Camilo, for the introduction. Firstly, I'd like to thank the organizers for the invitation. It's great to have the opportunity to talk at IS. I mean, unfortunately virtually, but still, as I mentioned earlier to Camilo, I spent 1 year at the IS and interacted a lot with Thomas. So I enjoyed the time a lot. And this work, actually the work was studied when I was at the institute, because I had to read a very long and difficult paper by Bedrosian and Masmoudi to get started. And I think the fact that I had 1 year at the institute afforded me the opportunity to actually concentrate on something like long and complicated to get started. So it's great therefore great to talk about this result at the Institute for Advanced Study. So today my topic is on the long-time dynamics non-invasive damping for 2D Euler, and this is all joint work with Alex Ionescu from Princeton, so nearby. So we consider the two-dimensional, so this is let me emphasize, this is 2D, okay, 3D is totally different. So this is a 2D equation, 2D Euler equation in the vorticity formulation. So you have partial T omega plus U dot gradient omega is equal to 0. And the U is given through the Beer-Savart law from omega. The omega is a vorticity field and U is a velocity field. So you firstly solve a stream function, which is Laplace inverse of omega, subject to certain suitable boundary conditions if you are in a bounded domain. And then you take this perpendicular gradient. So for this equation, it's well known that smooth solutions remain smooth for all times. So there's no issue. There's no issue with regularity, where the solutions are, unless you consider quite sharp initial data. Otherwise, smooth solutions are smooth. No issue with regularity. And here the difficulty is the long-time behavior. So we want to understand how the solution behaves. So essentially, as t goes to infinity, what is the omega? What is the behavior of omega? So from the equation, you see that omega is transported by a velocity. So it's a transport equation, essentially. It's transported by a velocity field, which depends on the vorticity itself. Okay, so that's kind of the equation. The transport equation, nonlinear transport equation. So the difficulty of long-term behavior is due to the fact that there's no global relaxation mechanism. So there's no viscosity. In general, there's no issue with, it's not that you will go to infinity, so stuff will not be going to infinity. It's like dispersion, there's no dispersion. So it's not clear what happens to the solution. As a result, there are very few results on the precise dynamics of general solutions. Here I mention several results in this direction. There's an important result due to Arnold on stability. So the equation actually has a tremendous amount of steady states, sometimes even finite codimensional manifold steady states. So you can find infinite dimensional manifold of steady states. So Arnold gave a criteria for stability based on variation principle. It's quite remarkable. It's pretty robust. It can be used to prove nonlinear stability for many steady states. But the issue is that there's no precise description of what the solution will do. Because, for example, that it will generally give you, for example, the solution will stay L2 close. Say omega will stay L2 close to a steady state. But you see that if you view that as your definitive stability, that's not definitive because for example, from this equation, it's trivial to see that the zero solution is L2 stable. Because if you just take energy estimate, multiply by omega and take energy estimate, so already that means to the extreme, Arnold's criteria will only give you that the zero is L2 stable, but you will not know how the small solutions behave. there's actually a precise result due to Lin and Zheng, who constructed the unstable manifold when your steady state is unstable. So then you can construct some finite dimensional manifold of solutions which converge backward in time exponentially to the steady state. But again, here the dynamics is non-generic because you only describe like 2 or 3 dimensional solutions. So although it looks like the dynamics could be completely chaotic, but it turned out that that's not the case. Okay, numerical simulations of mostly slightly viscous 2-dimensional flows often show some striking dynamics. In particular, one can often observe two processes. The first is so-called axisymmetrization of vortices, and the second is the so-called merging of the same sign vortices. And we now understand at least the mechanism. Okay, maybe not the full mathematical details yet, but at least the mechanism of the first process. Whereas for the second one, I think we are still pretty far from mathematically understanding it. In fact, even in physics literature, it doesn't seem that physicists actually understood how this happened. So this is all for about 2D dynamics. Real fluid is 3D. Okay, so the results are somewhat limited in physical meaning. But I would like to mention that actually, surprisingly, maybe that what you see in the numeric simulation, you can also see for the 3D flows, especially in large scales. So in many cases, when the 2-dimensional features are dominant, actually this is not too bad, at least in a larger scale equation. So here I'm playing this little video due to Theodore Drivas. So this is a 2D Euler on a periodic box, periodic torus. So you have some vorticity distribution. So the different color indicates the sign of the vorticity. On the right, you have stream function distribution. And you see that the really quite remarkably, initially the distribution is kind of random, but the small blobs of vorticity is quickly axisymmetrized by the bigger blobs of vorticity, and so kind of that leads to a simplification of the distribution of vorticity, and very quickly, not for too long time, you will only end up with two bigger vortices, and the smaller ones are so. So you can see the two things. Firstly, the bigger one can eat up the smaller one by the so-called axisymmetrization. So it just axisymmetrizes the small perturbations. And sometimes...
Excuse me, can you explain what you mean by axisymmetry?
So, okay, so maybe let me see if I can... so for example, if you look at these two guys, so the smaller one is... so symmetry, actually maybe this is 2D, so maybe a more precise way to say it is radialization, because if you have a small perturbation, this small perturbation is filamented by the bigger one, and then it ends up being a radial profile. So everything in the end becomes radial.
I'm sorry, I didn't understand. Can you repeat it again? What?
So if you look at like a small perturbation of this round vorticity distribution, okay, radial one, and then you have some random perturbation. The perturbation will become, in the end, it will become radial, right? It will become radial, and just like a cloud. Initially, it's maybe supported at some corner, and then it's transported. But so it's transported like rotated around the center profile. But the point is that the angular speed depends on the radius. So in the end, so if you are closer to the center, you rotate it faster. If you are further away from the center, you rotate it slower. So that differential rotation ends up like make this small patch like in the end become a radial profile.
A what?
Radial profile, like become round.
Okay.
Okay, so that I think the key is the differential rotation. That's the the rate of rotation depends on the radius. Because if you have uniform rotation, of course, if you add a small patch somewhere here, it will always be just, it will keep its shape, right? But because of the differential rotation, actually it will become radial.
What is there a power law for the ratio between the velocity, the radial velocity, and the distance to the?
Well, it depends on the detail of the initial of this bump here.
Okay, so it's
if it's like point vortex, like if you are pretty far away, yes. If you are pretty far away from this bunch, then you approximately there is a power law for the speed. But if you are close, of course, that sometimes can see the details.
No, I mean outside. It kind of looks like a gravitational model. If you close your eyes a bit. So if you're like outside of this small atmosphere of the vortex, does it behave like a power law?
That's right. Yeah.
Thanks.
Okay, so this is what I mean. You see that it's already the time is now pretty long for the simulation, but you only see these two. They will never merge because they have different sign. But if you have the same sign, they actually could merge. So this is what one observed, and we try to understand it. But as I mentioned earlier, so there are these two processes. But the second one is highly non-trivial because in the second, the merging, you have two potentially of same size, two vortices of the same size. And then the merging process, if you observe very closely, is firstly they have this connection. They make a long connection, and then there's some really non-linear process. And that seems to be very difficult to analyze. But the first one, Vertexsymmetrization, that we understand quite well. I mean, at least in terms of the mechanism. So that's what we will talk about today. So therefore, we now focus on the perturbative regimes and try to understand the dynamics near steady states. So we will consider two families of steady states. The first one is the shear flows. Okay, so the first one is vortices on R2. So these are vorticity distribution on R2 in R2 where the vorticity function is a radial function with respect to some center. So for any such functions, radial with respect to a center, if your vorticity is given like that, then it's a steady state. So you have many steady states. The second class is the shear flows. So these are flows on periodic channels. So it's like parallel flow. The flow is only in one direction, where the speed depends on the vertical direction. The flow, the velocity is on along the horizontal direction, and the speed depends on the vertical direction. So these two share many similarities because basically here you have the angle. Right? Angle is periodic. Here the x is periodic, so x is periodic. So here basically x plays the role of the angle in the radial case, in the vortex case. So the stability of these steady states is analysis of these steady states is a classic topic, and there are many big guys who already studied this at the beginning of almost like hundreds of years ago. Initially, they focus on the so-called mode stability. You linearize, try to see if there's some unstable mode. That's an ODE analysis, basically. And then more recently, people study linear stability because, okay, without unstable mode, you could hope to have linear stability, but that's not automatic. So there's some analysis involved, and more recently, also on nonlinear asymptotic analysis. So recently, there have been some tremendous progress on both linear and nonlinear analysis, which we will discuss today. So let me just mention that for the Vertexsymmetrization problem, the general case is still open. So the general case meaning that you take a radial vorticity distribution, let's say it's strictly decreasing. So vorticity as a function of R is decreasing in R. So that's the most, probably the most natural situation. In that case, to establish rigorously nonlinear inviscid asymptotic nonlinear inviscid damping is still open. So the picture that the video that you see, that we still cannot establish fully. But on a linearized level, this has been proved by Bedrosian, Kuti, Zelati, and Vico. So if you linearize around such a like a radial profile for the vorticity, assuming that the profile is decreasing in R with some other natural conditions, you can prove that the perturbation will decay to zero. Okay, so in fact, this linear analysis is already quite lengthy and difficult. The paper was like 120 pages long, and I think some simplification is needed to understand even at the linear level to extend nonlinear analysis. And okay, for nonlinear result on the whole plane R2, now we can only show on the nonlinear level, we can only show what we see in the video, assuming that the background vorticity is a point vortex. So omega is just concentrated at the one point.
So this is without dissipation, right? You have no dissipation here. This is really a Hamiltonian system.
Right.
And so usually when you want stability of a Hamiltonian system, you need something like KAM or something like that, but you're not using that. So you have some kind of radiative mechanism here, or what?
The mechanism on the Fourier side is that the energy is transported in the Fourier side to infinity.
So you couldn't do this in a bounded region, for example, right?
We could do it on the boundary region. Yes, it is actually. Yeah, it is actually. You can do it on the boundary region because the mechanism is energy is escaping in the Fourier side.
Okay, so it goes into high Fourier modes.
Right.
Okay.
Yeah, exactly.
Yeah. Okay. Yes.
Okay, so to state the result, let's consider a vorticity distribution of the form given by like some kappa time Dirac mass. So this is the background vorticity. It's given as a Dirac mass plus a smooth perturbation. Okay, we assume that the perturbation does not touch the Dirac mass. So these two are strict. So PT is outside of the support of omega. In that case, the perturbed Euler equation can be written like this. So basically, you have the same Euler equation, except that you have one more term, which is the vorticity, the velocity generated by this background vorticity field. So at first glance, it looks like it's actually more complicated than 2D Euler because you have this one more term. But in reality, this is much simpler than 2D Euler because this term implies that the velocity or the stream function will decay. Okay, so this gives you a decay mechanism. And also the PT, because omega, you have some perturbation omega, PT can move. PT might move, so PT moves according to this law. It moves along the velocity determined by the perturbation. And in this case, okay, this equation can be rigorously derived if PT is outside of the support of omega. And this support condition is also propagated dynamically by the flow. So this is kept, this condition is preserved. And in this case, we can show what we see in the video.
So could you back up just, I want to make sure I understand this, because I guess this is the main point. You're going to perturb a point vortex moving in, this is the position and time, PFT.
Right.
And if omega is equal to 0, then what equation does that satisfy?
If omega is equal to 0, then of course there's no equation here, right? And then this is also 0, so nothing moves. So
nothing moves.
Okay. And PT will be just P0.
Okay, so it doesn't move as a function of time. Yeah.
Right.
So the time dependence will be due to the omega.
Right.
Okay.
Right. Yeah, omega on the one hand, so omega could be initially concentrated at a corner, and then because of the differential rotation generated by the Dirac mass, so that will be axially symmetrized. So that will kind of, initially it's here, but then it will permeate along a kind of annulus. So then it's kind of averaged over there, this omega. And the PT could move because of the perturbation. PT moves, but we'll see that the motion is minimal.
Now you're in R2? You're
yes.
in a plane?
R2. Now it's in R2, but nothing is kept to infinity. So everything is concentrated in a finite region. Nothing is kept to infinity.
Okay.
So my result is the following. So you have in a vortex case. So for just take the setting as I mentioned earlier. If you assume that the initial perturbation is small, actually in Jeffrey space. So this is in Jeffrey 2. Somehow unfortunately there's this very strong requirement for this mechanism to work, that the perturbation has to be extremely smooth. Then there's a unique solution for the system, and moreover, the position of the point vortex will stabilize to a final place extremely fast. In fact, almost exponentially fast, and omega will converge weakly to a function which is radial. So that's symmetrization I talk about. So initially it's concentrated.
Sorry, what do you mean by the bracket between psi and eta?
Sorry, where is it? Oh, this is the Fourier transform. Sorry, that's Fourier transform. Omega naught is a function of xy. You take the Fourier transform. This is theta means Fourier transform, and then Fourier transform of the variable x sine.
So the bracket of psi eta is the square root of 1 plus the modulus of the two-dimensional vector square.
Oh, this one. Sorry. Yes, that's right. Yes.
Okay.
Yes.
Okay.
Yes.
Okay.
Yeah, this is the kind of the Japanese bracket. You have 1 plus psi squared plus x.
Yeah. Okay. 1 plus psi squared plus eta squared and square root of that. Okay.
Right. Yeah. Thanks. Yep. So this is the vortex symmetrization in the special case when the background flow is a Dirac mass. So this is exactly what you see. You have a Dirac mass, some perturbation, smooth perturbation away from a Dirac mass. And then you let this evolve. Then the Dirac mass will start moving, and then on the other hand, because of differential rotation, what is closer to the Dirac mass will rotate faster. Outer layer will rotate slower. And then the support will permeate annulus. Okay, and then and actually weakly converge, not weakly but not strongly, weakly converge to a radial profile, and this point vortex will converge to a point P infinity. And then the perturbation will symmetrize around the final position. So that's what dynamically what happens in this case.
So let me ask you another question. So you start with a very, very smooth perturbation,
right?
And then your solution always remains of the form as a Dirac mass plus some kind of perturbation, which remains Dirac.
Actually, that's an extremely good question. So actually, it's not going to be, the perturbation will lose regularity extremely fast. Yeah, because it's only in the end we are weakly converged, but not strongly converged.
Yeah. So you're
in our direction.
There's some high modes that are escaping.
Right. Yeah. So you can imagine, right, that you have the differential rotation. So what is closer to the center is rotated faster. What is out further away from the center will rotate slower. So you have this, that creates a large derivative in our direction as time goes to infinity.
Yeah.
So we have to look at these things very carefully in carefully choosing coordinates. But remarkably, when everything in the end weakly converges to a final profile, the final profile is actually Jeffrey. So omega t, they are qualitatively Jeffrey, but with extremely bad norms. But then you take the weak limit, the limiting function is uniformly Jeffrey, is Jeffrey too.
But as you let time go on, as your rate norm just starts to blow up or what?
Right, the Jeffrey norm of omega t will blow up as t goes to infinity, but the weak limit will be smooth, Jeffrey. Yeah. So we'll see what happens more precisely for the shear flow case, which is kind of similar to this. This is what I just want to mention because it has a direct connection with the video I played, but I will not actually give the detail of how this is proved. Rather, I will give the proof for the general shear flow case. Okay, so that's what happens for the point vortex. Of course, we would like to show this for the general vorticity profile. So general vorticity profile is a vorticity distribution which is radial and decreasing in the radial direction. That unfortunately is still open problem. Okay, but now let's turn to the case of shear flow. So the shear flow is a parallel flow on a channel. In a channel, the flow is only in the x direction, and the velocity, the speed depends on the y direction. So we want to assume that B is say either strictly increasing or strictly decreasing, monotone shear flows. So we consider x to be periodic. So this is connected to the analogy with the vortex case, because we want to view x as the angle theta. So x is periodic. Y is in a channel, so that would correspond to an annular region. And we'll see that this is not surprising, because we cannot handle what happens exactly at the center of the vortex in our R2 case. That's exactly so. By working with this channel, if you view x as theta, then the channel is like annulus, right? So you avoid the difficulty with the center. So the center of the vortex, that's what prevents us from proving similar result as the point vortex case. So if we perturb this, okay, so this is our background flow with this is as the vorticity, this is the background vorticity, perturb it with u and omega, then the perturbation satisfies this perturbed Euler equation. Okay, and then the u again is determined through the Beer-Savart law. So we want to study this equation, and basically we want to understand what happens as t goes to infinity. So again, it looks at first glance, it looks like this is more complicated than the 2D Euler because you have two more terms. But again, these two terms give us a stability mechanism. So let's recall to state our theorem precisely. Let's recall the definition of Gevrey spaces. So basically you take the free. There are several equivalent ways of calculating Gevrey spaces. But for us, we have to work with Fourier transform version, because in a physical space calculation, it's easy to lose the constant, and we cannot lose any constant here. So you take Fourier transform in both x and y, and then you multiply this almost exponential weight, right? If you, that's give you Gevrey norm with parameter lambda and s. So if you this is of course really big, right? If you for our favorite Sobolev norms, you wouldn't have no e here, right? You would have just k side to s power. That would be your favorite Gevrey space. But here we have to have this exponential weight. If s is equal to 1, of course that would be analytic functions. So we will generally, for us, we will work with s is equal to 1/2, which turns out to be the sharp space for this purpose. So we also have to have some conditions on the background shear flow. Basically, it has to be monotone. And okay, this is an important technical assumption that B has to be linear when you are close to the boundary. Y is equal to 0 and y is equal to 1. So this turns out to be a critical assumption that we have to have in order to avoid the so-called boundary effects. The boundary effects turn out to be actually quite serious, even for, we all know that the boundary effect is serious if you have Navier-Stokes, right, with small viscosity, and especially in the vanishing viscosity limit. But it turns out that for really refined analysis for 2D Euler, even the boundary effect is also extremely complicated. So this will guarantee there's no boundary effect, no significant boundary effect. And also we assume that the background flow is Gevrey too. So the flow is extremely smooth. And also
periodic boundary conditions, would that avoid any problem like that, or is there a problem with periodic?
Periodic would not be compatible with this condition, because that's always some sort of issue. Yeah. But you can work with the whole space. You can also work with whole space. That's actually the original setting of Bedrosian and Masmudi, to work with the whole space. but then everything will have infinite energy. So there's always this little issues that's here. Okay, and also we have to assume that the linearized operator has no discrete eigenvalues, because otherwise the linearized flow will not be stable, right? So this is a natural condition. And under these conditions, we can show that if you have a perturbation of the shear flow, which is supported away from the boundary. Again, this is to guarantee that there's no boundary effect. So supported away from the boundary, and a small in GV2 norm. So it's very small in GV2 norm, and then you consider the solution. The solution is uniformly okay. The solution will uniformly supported away from the boundary. So the omega t will never. So initially it's assumed to be supported away from boundary, and then this condition is preserved for all times. So there's no boundary issues for all times. And also we know that you have in this equation, the dominant term is this guy, right? This is the dominant term because you have very significant, this is a transportation in X. Again, it's a differential transportation because By is increasing in Y or decreasing in Y. So the speed of transport in X is depending on Y. That's corresponding to the differential rotation. Because of this differential transportation, omega will not have uniform regularity in Y. Rather, if we want to get some object which has uniform regularity, because we want to do perturbation analysis, we have to catch an object which remains smooth for all times. So it turns out that a correct object is F, which is this object. Okay, this object basically omega is not good because omega has no uniform regularity in Y. But if you remember all the transport in the X direction and make this changing variable, okay. So you see that the transportation in X consists of two parts. The first part is due to the background flow, but then you have another part which is given by the nonlinearity. The nonlinearity is also a transport. It has transportation in the X direction and transportation in the Y direction. So here you remember all the transportation in the X direction. Okay, then you kind of undo this transportation in this changing variable. Then this becomes a smooth object for in both X and Y for all time. Then this actually is under control in GV2 and actually converge to a final profile, which is GV2 with an explicit rate. So that's actually the main conclusion. Then the next conclusions are kind of corollaries. So basically, you have convergence of the velocity to a final shear flow, okay, the X direction velocity converges to the mean velocity, and the Y direction velocity goes to 0 with the explicit rate. So that establishes the so-called inviscid damping, that you perturb a shear flow like a parallel flow, it will end up with another shear flow. Okay, so the result doesn't seem to be surprising, but the process is extremely violent because you lose the vorticity will become extremely rough if you do not look at it in the right frame of coordinates. But if you look at it in the right frame of coordinates, then everything is smooth. Okay, so that's kind of the picture. Okay, so I have some remarks about the result. Firstly, I have already mentioned this, that the support condition are necessary to avoid boundary effects. And the spectral assumption that the linearized operator has no discrete eigenvalues that can be guaranteed if, for example, B prime is bigger than or equal to 1 and the triple derivative is strictly less than 1. So in general, of course, if the linear operator has eigenvalue or not, discrete eigenvalue or not, that's a computational question. Right? Sometimes it happens, sometimes it does not happen. But if we have this size restriction, then there's no possibility of generating discrete eigenvalues. The GV regularity is also quite likely sharp. This is there's some result by Yuden and Masmuri, who showed that if you perturb not in GV2 but in a space which is logarithmically weaker than GFR2, then there's no hope to establish this kind of result due to a so-called echo event, echo phenomenon. Okay, I will not discuss that, but if you perturb in an even low regularity space like H2, okay, so or H1 for the perturbation, then we know definitively this result is not possible, because for extremely low regular perturbations, actually the linear operator will become bad. In fact, the perturbation could make the linear operator generate the eigenvalue. So that, of course, definitively destroys the mechanism. So at the qualitative level, so the theorem is quite quantitative, but at the qualitative level, the conclusion is consistent with a quite big conjecture. I mean, kind of quite a general conjecture regarding the dynamics of the 2D Euler. So I learned this conjecture from Vladimir Srak. So basically, the conjecture said that generically, the solution to 2D Euler will weakly but not strongly converge in L2. So you always have this mixing, so you will lose regularity. So omega t will not strongly converge, but only weakly converge. But it could converge still as t goes to infinity. So for us, omega, so this uniform control actually implies that omega weakly converge to a function which only depends on y as t goes to infinity.
I would like to go back to this conjecture. I want to make sure I understand. So this is not just this is even in bounded domains, right? I mean,
that's right. That's right.
So it would converge to one of the steady states, one of the known steady. Well, no, it would converge to a steady state.
Right. Right.
Okay.
So basically, like your energy will escape in the Fourier space to infinity. Some part of the energy will come. So, okay, some part will settle down. Okay, the energy, total energy, some part of it will settle down to the low modes. But then there's always generically there's a portion of energy which escape to Fourier infinity. Okay, so in the remaining time, maybe I have like 15 minutes or so. Let me just briefly go over some of the key ideas of the proof.
Sorry, can I ask one question before?
Yes.
So like in the point vortex case, the limit, the omega infinity was radial.
Mm-hmm.
In the shear flow case, does the limit has any structure or like?
The limit will be another a function depending only on y.
Ah, I see.
That actually follows from here, because if you take a Fourier transform in x, Fourier transform in x, omega will always carry this oscillatory factor. So the oscillatory factor will make it weakly converge to 0. Okay. It's like you have Fy e to I kyt. So Fy e to I kyt will converge to 0 as t goes to infinity weakly.
I see.
Yeah.
Okay. Thank you.
Yep. Okay. So for the proof, there are 3 main components, because this is a perturbative analysis involving a non-trivial linear operator. So the first task is to understand linear evolution, but this has to be understood in the context, in the right context for the nonlinear analysis. Because for nonlinear analysis basically determines what kind of space you have to work with, and that dictates also for which space you have to work with the linear flow. So this is turn out to be GFR spaces. And then for the nonlinear analysis, again, we have to, because the vorticity actually will lose regularity, so we have to look at the vorticity in the right way, basically by making a nonlinear change of a coordinate and look at the profile with respect to these coordinates, and then prove uniform regularity for the profile. And thirdly, we have to somehow combine the 2 analyses together. So here it's a quite interesting idea is to somehow, remarkably, the linear and nonlinear dynamics turn out that you can completely decouple them. So that's kind of interesting, which I hope to be able to discuss. Okay, so let's start with the linear theory. So this is a linearized. The linear equation is actually decouples in the Fourier mode in X. So you take Fourier transform in X. Firstly it's to begin with it's a PDE, but then you take Fourier transform in X and it becomes a countable family of ODEs. So because the Fourier mode in X does not interact with each other. Okay, so you get this equation where the psi k is determined by omega k by solving this elliptic equation. So actually now you see that the decay mechanism is from these two terms. Okay, this term is important, but this is not the main term. In particular, if you assume that b double prime is equal to 0, okay, if b double prime is equal to 0, then this equation can be solved explicitly. Okay, so omega k is simply given by omega k 0 e to minus I k tb. And then, of course, you can recover the stream function using the vorticity function by integrating against the Green's function, which is this. And you see that this guy, for this you have decay. So the decay of stream function is the key. Okay, so let's see why you get the decay. Well, you have Green's function, and then you have the this oscillatory integral. So basically, this is an oscillatory integral. And then if you want to get the 1 over t squared decay, you just have to integrate by parts twice in this integral. But so you get 1 over t squared decay. But you also see that it is not possible to get more than 1 over t squared decay because the Green's function is not very smooth, right? The Green's function, if you take two derivatives in the Green's function, you get a Dirac mass, and that's it. So this is the best you can do. So that gives a sharp decay rate. And generally, if b double prime is not equal to 0, of course, we have to analyze this linear operator, which is given like this, because the psi k is given by the integral of omega k against the Green's function. So this is exactly the operator here, modulo the I k factor, which is okay. You keep track. Okay, so this is a linearized operator that we have to deal with, and then. So then we try to kind of extend this kind of analysis to a more general linear operator. And this has been done by Weizhang Zhao, who proved the sharp estimates. So basically, the sharp estimate is that stream function decays like 1 over t squared. Derivative in x doesn't really matter because it translates to ik psi k. It doesn't really mess up with the decay. But derivative in y will mess up the decay. You will have one less rate of decay. This can also be seen from this formula, because if you take a derivative in y here, the derivative will fall on the Green's function. Okay, and then the Green's function, you can then, if you want to integrate by parts to get decay in t, you can only do integration by parts once now, because you have partial y gk already. But if you take one derivative, you will already hit a Dirac mass. So that's why partial y of psi only decays like 1 over t instead of 1 over t squared. So these estimates are all sharp, and Weizhang Zhao proved them in L2 space. But unfortunately, these estimates are not sufficient for nonlinear analysis, because this is like dispersive estimates for dispersion equation. But you have a quasi-linear equation. You have to be much more careful with respect to these estimates. So to see what would be the right estimates, let's again look at the simple case when by is equal to y. So the correct case, the simplest flow. In that case, then you have this equation, which can be solved explicitly. So you have this as a solution. You take Fourier transform in both x and y, then the stream function can be written like this. Okay. And if you, so now then it's clear that it is not uniformly regular, because as t goes to infinity, you see this guy will so this will only have like 1 over k squared, 1 over psi squared decay. But if we want to make a uniform decay in psi, we can make a changing variable. So just like what we indicated earlier, so make a changing variable like this, then this phi will have Fourier transform of this type. And from this, you can read off the 1 over t squared decay rate, because as t goes to infinity, if k is not equal to 0, as t goes to infinity, this guy will be like 1 over t squared. Okay, so that gives you for fixed k, fixed psi, this like one, this goes to 0 as 1 over t squared. So that's the decay rate. But actually, more importantly, it is extremely critical to keep track of this decay factor, because you can already see that if you want to convert this decay factor into a pure power type decay factor like 1 over t squared, you have to lose something, right? Because this is not, because when psi is equal to kt, this does not really decay very much. So if you want to dominate this guy using something over t squared, the something will have to be of the order psi squared. So that's a huge loss in psi, therefore a huge loss of derivative. So for the nonlinear analysis, we do not have any luxury to lose the derivative. So it's important to keep track of this factor. So for nonlinear applications, for the general shear flow, we want to have estimates similar to this. So it turns out that that is possible if we work with a new coordinate in a variable z and v. Okay, v which is by and z as x minus tv. So this is related to the undoing the transport in the x direction. If you work with zv variable, then we have the uniform estimates exactly like this. Okay, so that's the key point. So let me just briefly indicate how this can be done. So to understand the linear theory, linear operator, we use spectral representation formula. So the stream function can be represented as as oscillatory integral against the spectral density function. So we will not have time to discuss how you can derive this, but you can imagine, right? You have a linear operator, you have evolution equation determined by the linear operator. So then you have the spectral representation formula, right? The spectral representation formula gives you the evolution, and so the flow is determined by integrating against the spectral measure, and these guys are your favorite spectral density for your spectral measure. So these are what this is. So so the question is how to characterize this spectral density function. It turns out that the spectral density function satisfies a nice PDE. Okay, so this is a PDE satisfying the spectral density function. So here you see that spectral density function has several parameters. Okay, k is fixed, but importantly, you have y naught, which is the spectral parameter, and y is the physical parameter. So you integrating against the spectral parameter to get the evolution. So now you have this formula. Then clearly, if we want to get 1 over t squared decay, what we need is to integrate by parts twice in y naught. So we have to understand how regular this is when you take 2 derivatives in y naught. Okay, so that's what we have to at least get. And then this is the equation satisfied by the spectral density function. So everything for the linear evolution, everything is encoded in the spectral density function. So I want to emphasize the importance of this this function, that everything you want to know about the linear evolution is determined by the spectral density function. And the spectral density function is not very smooth. Okay, the critical role is played by the singularity of the spectral density function. And the fact that the spectral density function is singular can be read off from the equation it satisfies. So this is the equation that it satisfies. And you see that there is a singularity here. Right? When y is equal to y0, it's singular. So that's why this guy cannot be expected to be smooth. And that's good because you see that second derivative of the spectral density function almost give you a Dirac mass. That's why also you can only get a 1 over t squared decay. So this equation has actually been studied classically, but I think one of the confusing points is that you see to get decay in t, you need to have regularity. You need to control second derivative in y naught in the spectral parameter. But the equation is formulated with the first parameter, with the first variable y. So the equation is an equation in y, but you need to have smoothness in y naught. So I think that's one of the issues which many people find confusing at the beginning of this analysis. So Okay, so I'm running out of time, it seems, but okay, so let me just speed up a little bit, just say how this can be analyzed. So basically, the difficulty is the singularities. But if you make a changing variable first by setting v as by, w as by naught, then the singularity can be simplified because the singularity now it has become v minus w. Okay, but okay, so then the resulting function will still be singular in v, both v and w, because the singularity is 1 over v minus w. 1 over v minus w is singular in both v and w. But the key observation is that if you now shift to v plus w, then the singularity of this guy is now becomes 1 over v plus I epsilon. So this guy in the end will satisfy an equation which is not singular in w. So it turns out that this guy is completely regular in w, very regular in w. That turned out to be exactly the right structure of singularity that one needs for the spectral density function. Of course, here this guy and this guy, they are related. There's a clear relation between the two. And this, v and this function is singular in y and y naught. But the question is, how do you kind of precisely capture the singularity? And there's a simple answer, which is that if you look at it in this variable, then it's only singular in one variable, but not singular in the other variable. So that turned out to be the exactly right calculation. Okay, so I will just take maybe 5 minutes to finish this. I think I started like 2 minutes late. I don't know if that's okay with you.
Sure, there's no problem. Absolutely.
Okay, thank you very much.
Go ahead.
Okay, so yeah, let me just take a few minutes very quickly to go over this. So now that is the linear analysis. To pass to nonlinear analysis, we have to use some more ideas. So this idea originally come from Bertolucci and Massimotti and adapted by Ionescu and I. So as we mentioned earlier, the vorticity function is not expected to be smooth for all time, uniformly smooth for all time, because of the transportation effect. The transportation will only mess up your regularity. Okay, you cannot hope the transportation transport to somehow help you with regularity. That doesn't really happen. So what we can do is to undo the transportation. So remember, so just to kind of track all the transportation and make a changing variable so that in a new variable there's no more transportation at least in the x direction. Minimize the transportation. So then you work with the zv variable. So z is the renormalized x, and v is the speed. Okay, the speed variable. Now in the new coordinate you have this equation. So everything you write in the new coordinate, this little f is omega in the new coordinate, and the phi is a string function in the new coordinate. Then you have this equation. But in this equation, because, okay, this is the co-ed case. This is the co-ed case. So v prime is of order 1, v double prime is small, and so on. So this allows us to make a simple simplification. So in the end, okay, after some simplification, we arrive at this equation. So this is actually a very good equation. This equation is self-contained. I think to understand the nonlinear analysis, this is the right equation to look at, because it's a self-contained equation. It's the simplest that still captures the main difficulty of the original system. So you still have a transport equation with some velocity, okay, like this, and the phi is determined through f like this, using this. And then this equation, you can expect that f will remain uniformly smooth for all times. This is because this guy will decay quadratically in time. Okay, the velocity field decays quadratically in time. So the total transportation is expected to be small. Okay, so all the particles, they will only move a tiny amount. So in the end, the effect on the overall regularity is small. So the major issue here is this guy, because if you take a Fourier transform, of course you have the explicit equation, so you can take Fourier transform and solve for phi. It is given as this, okay, and then you see that this decay. So firstly, there's good news, which is that you have a decay factor. You can expect that you have 1 over t squared decay for the velocity field, which implies that in general the transportation will not mess up with your regularity very much. But on the other hand, this is not very small. Okay, so especially when t is equal to psi over k and psi large, this could be a really large factor. And that's a really difficult issue. And to resolve that issue, the idea is to define some sort of energy functional, to use the energy functional to control the profile function. So the energy functional is, okay, it's kind of a general idea that you take some weight function and then you take the Fourier transform and estimate how big this is. I am running out of time, so let me just mention that so there are 2 kind of key features for this weight function. The first important feature is that it's decreasing in time. Okay, so you have transport effect. The transport will tend to decrease the regularity of your profile, okay, because of the transportation. So you expect your F to lose regularity gradually over time, but you also make the weight decrease over time. So in other words, you measure this function which loses regularity with weaker and weaker norm. So in the end, there's this balance. In the end, you hope that by measuring it with weaker and weaker norm, you can still achieve that the goal that you can have uniform control on the energy function. Okay, so that's the number 1 idea. And number 2, to deal with this issue that you have a large factor here, we want to define a norm with the weight which is imbalanced. So balanced weight is a weight which when you change the parameter by 1, the size of the weight does not really change very much. But imbalanced weight are weights for which if you change parameter even just by 1, the weights will change significantly. So somehow in this nonlinearity, there's this imbalance between the frequencies that allows you to shift from one type of weight to the other type. And when you make the shift, actually there will be a large factor that you can absorb by designing this imbalanced weight. So that's another idea. But in the end, what you can achieve is that you can control this energy functional for all times, and that allows you to control the flow. Okay, so maybe I should actually stop here. Unfortunately, I'm not able to will not be able to cover the last idea, so which is how to deal with the linear. So to couple these 2 things together, linear analysis, nonlinear analysis. But hopefully, if you have questions, some of you are interested, I can definitely address it in the question session. Thank you.
Thank you. Questions? May I start by asking? One question, just kind of on the general side. So if you go back to the initial picture, right? So the one that you sort of showed us in the simulation.
Mm-hmm.
So in there, I guess, is it correct that you see that, like, there is, I mean, one big vortex is like attracting positive vorticity and one big vortex is attracting negative vorticity, or am I?
That's right. I think that's basically right.
That's right. Yeah. So now in your in your cartoon, well, I actually have two questions in the end. So in your result, you have just one guy, right? And everything is gravitating around it.
That's right.
Doesn't seem to play a role whether the vorticity is positive or negative, right?
No, that's right.
It will always symmetrize.
Right, because yeah, exactly. So in our setting, we only have one blob. There's no other blob.
So could you imagine now to go? I guess this might be extremely complicated, but could you imagine to go one step further and like say, okay, I have 1 point vortex with positive vorticity, 1 point vortex with negative vorticity, and you try to carry on the same analysis, and these guys, they're spinning around and you're attracting.
That would be extremely interesting. I think.
Somehow, what is not so clear to me is by which mechanism the negative part is going towards the negative point vortex, and the positive part should be going towards the positive point vortex, right?
Yeah, so yeah, that's exactly. So
there should be a mechanism like that, but what is it doing it actually?
That's a really good point. So you do have this Pavarenti and what is the other guy? You know the paper, right? By Pavarenti and another guy on the point vortex system.
Yeah,
so we do.
Yes.
Yes, we do have some coercivity making these things separate. You have some mechanism to have them separate, but just like variational kind of things.
Yeah, they have some repulsion, I guess.
Right. But then, okay, that's a good thing. So the two, in principle, the two pieces will be separated, and then for each piece you have this vortex symmetrization. But somehow they will never interact. I think the difficulty is how to quantify the interaction, because this configuration will move for all times.
Right. But not only that, no. I mean, if you perturb it with something negative and positive, for some reason the positive guys are going one way and the negative guys, they will be going the other way. Okay, I guess they have an attraction, positive attraction.
Right. Yeah, they will not totally get away, but okay, that's extremely interesting. But okay, so you have to be on a bounded domain, like in a periodic domain. Otherwise, they may go away.
They will go to infinity.
Right. Otherwise, they will go to infinity. But in a periodic domain, they will not go to infinity. But this the whole, I don't know how difficult it is actually. But that's extremely interesting. It would be wonderful if one can show that that this picture is okay.
Mm-hmm.
Yeah, but I don't know how difficult it is.
Other questions?
Well, I was just wondering, I mean, I know many of these stability results require, this kind of Givray class, and you were explaining a little bit about what happens if they were less regular. But physically, would you really expect it to matter that much?
Yeah, that's a very good question. Okay, so in reality, you always have some viscosity, right? The viscosity will make everything extremely smooth, very smooth.
And that smooths it out immediately.
Yeah, but actually, that's what happens. I mean, we know that if the perturbation is not as regular as GFA2, then the without viscosity, what we prove here is not going to be true. But what is not clear is what exactly happened in that case.
Yeah,
so you might not have
viscosity. Do your results become much simpler, or can you formulate results with viscosity, or not?
Oh, with viscosity, it's not trivial actually. With viscosity, it's not going to be trivial.
Yeah.
In fact, I think it could be a little.
You have to worry. First of all, you have to worry that the thing just goes to zero, right? I mean, if you wait long enough.
Yeah, because now you have two mechanisms. One is axisymmetrization, and also you have the viscosity, which gives you damping. So
yeah.
Everything is time dependent. The background
so
of
you have to work
time dependent.
Time scale.
Right. You have to divide the time scales.
Yeah.
And presumably, the optimal result would be a result where your theorem depends on the viscosity, but as viscosity goes to zero, you recover the same result.
That would be very nice. Maybe that's hard.
As far as I know, only in the correct case, that's okay. And that was done by Bertozzi, Vicol, and Masmudi.
Yeah. But
the general case is more complicated because your background. So in the correct case, the correct flow is a solution for both to Euler and Navier-Stokes. But for general shear flow, if you have viscosity, then the background flow will be time dependent. So you have to divide that. I think it's just a lot more complicated.
Yeah.
But that's, I mean, it's a meaningful question. I think it's a very meaningful question. It's just that everything is so complicated in this business that people select the easiest among all these monstrous problems to solve first.
You have to do what you can, right?
Right.
Very, very nice talk.
Thank you.
Other questions? Well, that does not seem to be the case. Yes, this was very, very interesting. Thank you very much. And
thanks. Thank you, everyone. Thanks for your attention. Sorry, I didn't finish everything, but if you are interested, just send me an email. I'll be happy to send you the